Hello.
Hello.
I seem to have some difficulty getting meeting started. Somehow keep going to different place.
That's what I was having trouble with like earlier. I came in a little bit late, and I'm glad that other people are having issues.
Today we're doing a practice, so I need you all have your computer up and running. And
got it.
So the first thing we do is we look at the. Do you see my screen yet? I didn't share.
No,
screen, right?
no. And we can't see your like self, but like if you want that or not, you know.
All right, share the screen.
Now we see you. Not the screen though. Now we see the screen.
So everybody there?
Yes.
So you go to the lesson. All right. And the first things I want you to start is this one. Neural network playground. Click on that link and get it running on and see whether you get something. So if I click this things, I'll see something look like this. And see whether you see what I have.
Yes.
Everybody there?
Yep.
Okay. So this is Google's running on Google platform. So it's running on TensorFlow, but it's very nice interfacing toy model to reinforce the concept, the big picture we talked about it in last 2 lectures, and this gives you some, hand-on practical experience. And then we later on do a little bit more detail using PyTorch. Okay, so what you see on the screen is, you notice a couple of things, right? You see 3 layers of neural network. That's the input layer. I have X1, X2, and then there's the intermediate layer, which is 4 neurons, and then output layer, which has 2 neurons, right? You all see that?
Yep.
Okay.
Yes.
Now you see a picture on the right, which is right, and the picture has a bunch of dots. There are blue dot and the orange dot, a yellow dot. All right. So our task is basically, you notice the on top right corner, that's called problem type. And if you click on that, it's either classification or regression, right? So we are now on classification. What that means is to say we want to classify. We want to classify a dot, whether it's belong to blue or belong to yellow. Okay, based on the input, and currently we only have 2 input, namely the X1 and X2, namely the 2 coordinates. So every dot has a 2 coordinates, so it's X1 or X2. You notice if you hover on X1, X2, so that is where is showing, whether it's a left on the right side, on right side, or top or bottom. So one is representing coordinate in X, the other one represents coordinate on Y. Now in general, the blue color is a positive, yellow color is a negative. So everything is it clear so far to you?
I think so.
Yeah.
Okay,
yes,
if you have questions, and ask, all right? Now on the top, you see the bottom, there's a running bottom, there's airport. Airport is basically say how many times we do running, right? Now learning rate, okay, learning rate, if you click it, there's a bunch of learning rate you can choose, basically increase it by order of magnitude. So I have here as point also. Now what do you remember this learning rate it means? Now remember the overall, the neural network setup say we want to do certain tasks, and then we feed it with some training, and they given particular data, feed into training, there's outcome, and outcome is different from the target. We take the difference with a certain measure, we call that loss function, and then we take a derivative of that with respect to all this connection, which is this wire, all this connection, all right? And then depending on that derivative, which is gradient, we do gradient descent, and then we increase or decrease that particular connection by a certain amount. And that certain amount is proportional to learning rate, right? So that is what the learning rate means, okay? Now the next thing you see that on there is the activation. You click on activation, there are 4 choices, either ReLU, Tench, Sigmoid, linear. Now let me explain a little bit of this 4 choice. Now remember we talk about sigmoid, right? Sigmoid. Now you look at my screen. Here is the difference between sigmoid and the ReLU. The sigmoid function, remember we talked about last lecture, is basically say, okay, a particular neuron take all the input, namely from early layer and with certain weight, and we can and then add a bias, we get the z value, and then we feed into z value into the sigmoid function to decide what is activation, where's output of this particular neuron going to is a descendant. All right, and this sigmoid function is based on an analog response of neuron. So in fact, if you look at the biologically, dig into neuron to measurement of its activation, it's something resemblant to this. So that's why this sigmoid function is originally for much of many decades used. Now, in modern version of this thing is ReLU. This is the most efficient one used. So you can see it's basically simplified to this. Now remember, original sigma function actually came from the step function. Now ReLU is evolution as sigmoid. You can see that it's basically flat up to 0 and is linear up to certain point. Okay, so in terms of shape, this had closely on the bigger picture, very much the sigmoid. And it turned out the ReLU is a particular. This is based on a analog digital device called rectification device. And it turned out this particular implementation is very easy, very efficient for calculation purpose. And the result is essentially not much different to sigmoid, but is much more efficient. Because this is the one of the very elementary calculation going into this neural network. So making this particular choice actually. So now there are other choices, which is like, for example, you can have Tench, which is basically Tench function. So you can see overall shape is also has the sigmoid function shape. And then of course, so those are some other choices. There are, I think, some more complicated so-called leaky ReLU, for example. So we don't need to go into detail. There are a bunch of other possibility of doing choice, but ReLU is the one, the rectifier linear units is the one which now is pretty much the standard for most of a neural network actually implemented. All right, so that is about ReLU. That now I go back to my now. So let's say let's stick with sigmoid for a moment at beginning on your computer. Let's not bother with regularization at the moment. This is something we haven't talked about it. So that so we leave this regularization none, regularization rate as 0, and the classification problem type we want to classify. All right. Now, as I set up at the moment, it's 2 input neuron, 1 intermediate layer 4, and 2 output neuron. Okay. So if I run, and then on the left there are 4 possible tests on the data version. So at the moment we're on the first one, which is relatively simple. You almost can guess, intuitively can guess to say, the things close to 0, 0, if you draw a circle, it's pretty much encircle this. And then the things outside is yellow. Right? Now, if you click some other data path, it's basically increasing complexity. So the next one, there are 4 problems. The next problem now, you basically have to divide it into quadrangle. And the third one is the, this is actually the second one, and third one there's a cluster. And the last one, of course, is much more complex. If you try to think about if you build them simple like x1, x2 input to classify, this will be very difficult. Okay. So let's start with first one. Go back to the first data. And on the left side, on that panel, there is a ratio. So after data, there's a ratio of training to test data. Right. So for this particular data, there are a bunch of points. We take half of this point to be for the training purpose, and half of that for verification part. Right. So basically say, okay, we use half of data, we know whether it's yellow and blue, and the rest of half, we will test our network to say whether actually it's able to predict yellow is yellow and the blue is blue. Okay, so that's what this percentage. You can scale this back and forwards of the different amounts. So for example here, if I scale ratio of training to data set 20%, then only make small amount of data for training. And so if I scale to the right, all the way to 90%, that is almost all the data for training, only 10% left for the verification. So I just started for 50%. It's easy to, okay. Now noise represent to say your input maybe is not precise, which has a noise. So that's for a moment, not worry about noise, all right? So we leave noise to 0. Now the batch size, which is the last slide bar, okay? Batch size is basically to say, now what we could do in the training is to say, I will take a point, I feed through, and I calculated the output cost function, and then back propagate. But that is not very efficient. So what you want to do is you do a bunch of these things together, and then average over, and then do the back propagation. So that's more efficient. So that's what the batch size means. So you can slide, choose between from 1 all the way to 30. So we choose let's say 10, just right. And with all this setup, and we can just run. All right. So if we run, and you notice the things is there's an output. All right. And you notice that loss function, test loss. What you want is the test loss function keep decreasing. You want to say, if loss function go to 0, that means you're very efficient. You can see it takes a long time for it to run, and you can see it take a while, and it's still running. And now it's getting better. It basically keep running these things. And now you see after a certain amount of time. So I'm going to stop, let's say, somewhere around 1,000 epoch. And okay, so I'm starting. So it kind of able to classify, basically say, depend on x1, x2 coordinate, or if x1, x2 happen to falling into that blue shaded region, it will predict is to be blue. And if x1, x2 coordinate follow into the yellow region, it will predict to be yellow. And actually, it's pretty good. All right. Can I see your screen individually? See.
You have to enable it.
So how do I do that?
That's a good question. I'm not really sure. It's just that it says host disable participant screen sharing.
Okay, now let's see, manager participant. So presumably I can manage a participant. Invite, mute, unmute. What else can I do? Mute participant, allow participant to unmute, play, extend, enable waiting room, lock meeting. That's not what I want. What else I can do? New share, block pause recording, disable participant annotation, show name associating hide video, share computer sound.
Maybe it's like.
Anybody know where I can let you to show me your screen, what it look like?
I think that next to screen, is there a little arrow to pop up next to share screen on your monitor?
Okay. I can say here, right? New share?
I can't see it. We can't see that, the Zoom options on your screen, but I'm pretty sure for the host, there's something next to the green share screen. And if I remember correctly, the option might be in there, or there might be another thing to click from there.
Allow participant to share screen. Okay, I find it.
Yeah. Mm-hmm.
It's under the security. Okay,
No,
how about one by one? Let's Brian first. See what do you get in your screen?
We cannot start the screen share while the other is screen sharing. That's what it says, or not specifically. So I think you need to stop sharing your screen, and then we can individually.
So I stopped sharing my screen?
Yes, I think so.
Sure.
Yeah, I think you're right.
How would I stop this now? Stop share. Okay, I can stop share here. Okay, now I stop my shares.
Okay. I guess I can go first.
Okay, you gonna go first. I just want to make sure you are all doing things.
You see this?
Okay, so you get a different shape than mine.
Yes, and I was messing around with it, and I thought because like you see how like this is kind of like polygonal, but
okay.
like if you switch over to these two right here, you get a perfect circle.
Okay.
And I thought that was interesting. Oh yeah. Let's stop the share.
I can go next.
Okay.
Let me see. Okay, do you see that?
Yes.
Yes, we see your screen. Yes.
Okay. For me, I think it stabilized to this a lot faster.
Okay.
It got to this shape in like just a few hundred epochs.
Now, because remember the data set is random. Your data set is different from my data set. They are generally random. So yes. Okay. And next.
I'll go ahead. So yeah, I used those to the x1 and x2 squared and got this circular shape in like maybe 50 epochs.
Now, the reason for that is notice also you're using ReLU, you're not doing Sigmoid. ReLU actually much more efficient.
Oh, I see.
Well, I was using ReLU too.
Okay.
Yes.
All right.
That makes sense.
All right.
Using TANH, TANH makes it all circular. Like on the X1 and X2.
Next. Thing.
That's.
Okay, all right, got a nice background picture. What is that?
Dan, we can't hear you.
We can hear you, yes. We see the background picture, Dan.
Bring up Notepad and like start typing stuff. Yeah, we can't hear you, dog.
He's doing something,
okay.
but it's
yeah.
Okay. Now we hear you.
Yeah. I was confused, like how to unmute the conversation. It's like I can't.
Now you need to try share your screen.
Wait, can you see my screen?
Well, we see the
desktop. Background. We don't see your browser.
Oh, that's weird because I'm opening the browser.
I think you need to share whole screen rather than share a particular. Yeah. Try to share again.
Let me see. How to new share? Let me see. New share. Wait. I'm confused how to do this. I'm not sure how to share the screen.
Well, do you have Firefox open now?
I have, yeah. I have
Chrome. Okay. Stop sharing your screen right for a second.
Okay. Stop
and
sharing.
then like try to open up the share screen thing again, and there should be like specific applications that you can pick what to share.
Let me see. Oh, share allowed. Wait, what is it right now? Nope, not this one.
I think it's the first choice of mine. If I choose the first choice, it basically share everything, not like individual browser or individual window.
Let me see share screen. I will share this one. Oh, okay. Share. I got it.
There you go.
Yay.
Now you all know how to do that. All right.
Yep. I was so
But you haven't.
yeah, because I changed the regular.
Okay. All right. So okay. That's okay. Result is not important. I just want to get everyone on that. And last one is Ray.
Two.
Yeah, so
Okay.
I
All
had
right.
like,
All right. Now you can stop the sharing. Get back to me.
okay.
What I want you to do now is, so I'm sharing only my screen now. I get to make the control. What I wanted you to do is to say, I'll give you 5 minutes to play this around. Just rely on X1 and the X2 input, okay? And you and everything else you can choose, number layer, number of neuron, and let's just make it easy, not too many choice. Let's just say everybody do the rule. All right, everybody do the rule, and then let's just do one layer or 2 layer at the most. Okay, don't go beyond 2 layers. All right.
Mm-hmm.
Either 1 layer or 2 layer, intermediate layer. So there's input, there's output. You can play around with how many neuron, and let's see what is the fast epoch you can get to 1%. Namely, the loss function go to 0.01. And then you stop there and then you just shout it back to say what number you get.
Okay. I'm getting the best I got right now is 80. The first one I had was like around 96 or something.
Okay.
44.
Wow.
Oh,
Okay.
well, how you get that 44?
I get everything sort of default with 2 hidden layers, 6 neurons in the first hidden layer, 3 neurons in the second hidden layer.
Oh, so you're adding, so you are doing 6 neuron in the first layer. All right, we try that. Let's say first neuron gets 6 layer. 1, 2,
I got 43.
and then second layer get 2.
3.
3, and the output 1 neuron or 2 neuron?
Wait, output. I think it's just with 2 hidden layers.
Yeah.
2 hidden layer, there's output layer, right? So total together is 4 layer. 1 input, 1 output, 2 hidden layer.
Yes.
Output is 2 neuron or 1 neuron?
Oh wait,
1 neuron.
I thought that last layer was a hidden layer. Where
Oh,
you
okay.
have 2
Maybe
right
that
now?
is a hidden layer. Maybe my bad. So okay, let's just take it up there. So basically, say, okay, it's a Yeah, that's right. So 2 hidden layer, that's right. 2 hidden layer. So it's a 6 and a 3. Is that what you're saying?
Yep.
Okay, that's good. Let me run on my computer, see what I get. I get 66. Somebody you get 44?
I think I had either the same configuration or like one very similar, and I got 43.
Okay, all right. Everybody there, Ray and Thian, I didn't hear you two make any comments.
I got like nearly 50, so it's close.
All right, now let's move on to the next data. So the left bottom, so there's 2 clusters, right? 2 clusters. Using exactly same setup where you get the most efficient, and then run for this particular and see how long it takes.
Still only using X and Y, or X1, X2?
Yeah.
With the same setup, I got to the loss of 0.01 in 18 epochs.
Yeah, so it's, well, for this particular setup, that seems to be the setup. It's very good, right? I get something around 20. So everybody get there?
Yeah.
So
Yes.
because this is relatively, if you look at data, it's relatively easy, right? If you draw a line, you know, and so basically there's a linear, the boundary is a linear line. So that I think is very easy to find. If you have x1, x2, then maybe x1 and x and y coordinate, you can draw a line pretty easy. Okay, now you go to the third data set where that's 4 cluster, and then run exactly the same thing. Now let's it's also on my computer it's also pretty efficient.
I had so I started running it, exact same thing, and I'm at about 300 epochs, and my training error is still like 25%.
That can be right. Maybe you want to refresh the whole thing. Like it's the rewinding button will restart everything from beginning, I think. Because of mine is okay, 6 2 hidden layer. First layer has 6, second layer has 2, has 3, and then it's only taking about 60 or so epoch to get there.
It sounds like you ended up in like one of those minimas or whatever where like it can't get out of. So
what do you got? What other people get?
I'm getting stuff that's like higher than 150, to be honest.
This is odd.
Hang on a second, let me refresh.
I think there's a lot of variance in this one. I keep running it over and over again, and sometimes it gets there in tens of epochs, and sometimes it never gets there.
Very 160.
Yeah, I think with
now,
3
so you can see now here it gets start. Now let's say let's now you allow you to play with a number of input. So there are 1, 2, 3, 4, 5, 6, 7 input. So let's say don't get too complicated. Stay with 2 hidden layer. Now you can add an additional flexibility of the input. right? And see whether you can get something reliably under 100. And now I want to do this total loss, not just 0.01, it's 0.001. So one more digit now.
I can get it in 25.
What?
Yeah, you just need to use x1, x2.
So you can see adding x1 square, I try adding x1 square, x2 square.
Yeah, but like the thing under x2 x2 squared, the x1 x2. So like the fifth from the top. In terms of the features.
No, okay, just keep running it, and we'll see at the end who win the competition, and I will ask whoever.
This is a competition.
Yes, competition now. Just say to get 0.001. What is your you know now remember that batch size remain 10. Okay, don't change the batch size because otherwise different batch size give you different result. Batch size remain 10. And you can vary whatever input you want. Stay with 2 hidden layer. You can change the number of neuron and see what is your best result. I can get to something around 100.
Well, with five neurons and 3 neurons, I got like 57. Yeah, 57.
And try again, see whether that's reliable.
Maybe if I regenerate, it might change though. Hang on a second. Let me refresh.
Is it test loss or training loss we need to get to 0.001?
Test. Well, odds are the training loss, in my experience, it gets to 0
I was looking
first.
at the test loss.
Got it.
500.
Because that is actually what relevant. Right? We want to know that how good it is.
It seems like this thing like would work like very well. Oh, wait, that actually doesn't. That neuron doesn't have anything associated with it. This is fun.
My best so far is 58.
And back to 60.
I got 45.
And reliably 45?
Around 50, I think. Maybe.
Oh, I put myself into a.
Yeah, I can get now around 40. Yes, yes.
No, I cannot get under 50. That's also because I'm just using x1, x2. So I'm gonna see if I can't improve upon this.
See anybody able to? Okay.
No, I can't get under like 50.
So best we have is about 40.
Mhm. Oh wait, I haven't tried moving around neurons. But again, down close, but it does look like 40's around where it goes
Ah, I
into.
get something which is 25.
Wow.
Now, I'll tell you one thing that I try. I vary the learning rate.
Well, that's cheating. You can't do that.
I didn't say we cannot change the learning rate. I just say stay with 2 hidden layer.
Mhm.
But 2 more minutes and then we'll stop and then move on to the next.
Mhm.
Okay? And just report what's your best result. By 1:13 p.m.
Yeah, I changed the learning rate and I got 13.
Oh, that's good. You want to keep that one. See what I know that one. Mhm.
I still get 40.
I got him 1.
Why you? I don't think that's true. You need to refresh your data. You probably is the same data. You keep learning, you get 1.
No. I'm getting 1, dog. I'm at 3 right now. And I got 0 test loss. I just got real lucky in terms of my starting values, I guess.
Refresh your data. You know, you can on the left, on the bottom
Yeah.
left, that's a regenerate. So that's
Yeah, I know, and I am. I'm now at 6.
oh, that look like you have efficiency. Efficient.
Well, also turned up the learning rate to 10.
Oh,
So,
you're just doing very high learning rate. I see.
for the higher learning rates, it's like it literally is just like a throw of the dice because you do have to like reset it
So high
multiple
learning
times.
rate. So now you can see high learning rate definitely is not very good. You know,
Like if you could get lucky, you get like
you cannot be.
really,
You have to be reliable. You cannot rely on the lucky. You basically has to be consistently getting that result. So of course, if learning rate is too small, things going very slow. If learning rate too big, you basically jumping around. So there is a optimal learning rate giving a particular neuron configuration.
0.3 is the best for me.
Okay, we stop here. Tell me all your result, your best result.
Hang on a second. Let's see if I can't.
I think like 38 was my best, somewhere around in the high 30s.
Okay.
About 39. That's my best.
No, okay, I am getting single-digit numbers consistently now.
Yeah, with a learning rate of 1,
Yes.
I'm getting consistently around like 4 epochs.
Okay, tell me what's your setup.
It's 5 neurons.
Which file as an input?
Yes, so the inputs x1, x2, and x1, x2.
What? X1 square and X2 square?
No,
So the
it's
first one down,
product.
the second one down, and the
Yeah.
fifth one down, and that's it.
Okay.
And then 5 neurons in the first layer.
So 3 input, 5 neuron in the first layer.
Yeah, and 3 output.
Second layer.
Yeah, 3 in the second layer.
3 in the second layer. And
And
learning
a
rate
learning rate of
of
1.
learning rate of 1.
Yes.
Let's see whether we can regenerate your result. Oh, that is very efficient.
Wow.
Yeah.
yeah, you have to use the
The
step.
single step button
So
next to it.
the key things, I think it is cross product input seem to be make a huge difference. Yeah, this input of X1, X2 seem to be make a huge difference.
Mhm.
That's very good. Now we take your architecture. Everybody adopt Matthew's architecture, and then move on to the last task, which is spiral. All right.
I was messing around with this earlier,
And then you can play around and see what is your best result. Now this is a very hard test. Now, so now instead getting 0.01, I just get to 0.01, just get to just get to the 10%, 0.1. Just, right? When you get to 10.1, you can, now 0.1 is not good enough. It may be 0.01. Get to 0.01.
Are they doing construction in your building, Brian?
Oh no, that's outside. Sorry.
Oh, no, it's fine. I was just wondering, like, why someone was trying to break your wall down.
I just got my window open, so.
Got it. Letting in the virus.
I don't think that I'm able to get 0.01. So,
Yeah, why is the energy landscape so, like...
because this is very difficult. This is something, you know, you had to draw this spider circle and they just, okay, you can try to a more hidden layer and see what you can get. So I'll just now say you can do anything you wanted and see what you can get something to 0.01. So my best result so far is 0.06. That seems to be all I can get within reasonable running time. What is the best guy you guys get?
I got
0.088 right now.
0.08.
yeah, it's similar to me.
And it's like
I-
it's fluctuating.
Anybody get it better than 0.06? Okay, now we can spend a lot of time doing this, but I want to stop here because this is lecture time. So let's stop here, come back to my screen. Okay, so part of the assignment, which I'm not making the official, is to say for your stay at home, if you don't have, if you have time to play around with listening, try to do whatever you can. See whether there's a way where you get to the 0.01. All right, and by next lecture, report me back, see whether you have a configuration or not, and they can share with us. This last task is difficult. Okay, now there's a whole other class of problem is called you know, regression. So, but they are kind of similar. But you get an idea of how, you know, this give you very good visualization of what's going on when you're doing learning. Basically, you can see those individual link. You know, when it's learning, you can see us. You know, here I start with something arbitrary, and then when you're learning, you can see individual link. Some of them going up, some of them going down, and they're getting heavier. So that is how back propagation work and strengthening particular connection, namely change those W, the weighting factor. And you can see, and then you also get visualization what the intermediate step, at least inside look like. You can see in the hidden layer, the pattern really does not have much to do with executive output. So, how exactly, there's no easy theory behind, what exactly the intermediate layer does. But so this is no surprising. It's just like, we have very difficult to systematically understanding what our brain doing things, how we synthesize all this input into our brain and then come out with a decision. That is just a very complicated process. So, it's on my screen, you are stopped at the 0.06. This is all I can get, seem to be. And after that, it seems to be not really convergent. It just fluctuate around 0.06. Now, presumably, if you guys play it around, you can come up with a neural architecture, with neural network architecture, which can get this classification problem resolved. But you get an idea of the bigger picture. You get an idea of qualitative how these things work. And what I want to do now is turn to coding now. Actually, write some code to see how these things work. Any more questions?
Nope.
All right, if not, then we just stop on this, and then you can play this on your spare time. Now you go back to my my lesson. So next, we'll go through this practice example with PyTorch for this handwritten digital digit recognition using PyTorch. Now, if you click on that, you should come up to this page. Handwritten digit recognition using PyTorch. Intro to neural network. Do you all get that?
Yes.
Yeah.
Now, have you guys looked into Colab and the PyTorch? Any of you?
Not Colab, but PyTorch.
Okay, get your screen running on Colab, which is basically Colab Research at google.com. Essentially, it's just a Python and the PyTorch engine, which you can run on your browser.
Okay.
You can do some simple things to make sure it's running. Like, let me see, new notebook. It's very much like, so that I can do, I say x equal to 3 and x. And I can just run it. So you see my screen?
Mm-hmm.
Yeah. Can you do something simply things like that?
Yes.
Yes.
Yeah.
I have 1, 2, yes.
Yes, I can see it.
3, yes.
Yes.
4.
I think I said yes too.
Everybody say yes?
Yeah, yes.
Yeah.
Is there a way for me to say that must be?
I haven't been able to get the. I might just be dumb, but I haven't gotten the notebook. How do you get the notebook up?
Well, it's not. I just go to Colab. Let's say, suppose we could go to Colab, either colab.research.google.com. It's on your browser. And you probably can just click any of these things. Let's say, welcome to Colab, for example. You get to this stage. And then you can just start with a file with new ones, a new notebook. Do you get to welcome to Colab page?
Yeah, I got to the welcome to Colab page.
And under file,
yeah.
you can start with new notebook.
So yeah, it's giving me an error. It's not letting me.
It's giving you an error. Share your screen.
Yeah,
Like-
okay. Okay.
That's weird.
Something funny going on with your computer. I don't know. I didn't have that problem.
Do you want me to share, or you could just?
So I need to stop sharing. Okay, yes. I stop sharing. See what's your share your screen.
Okay. So.
Are you using a? I'm using a Google browser. Okay, you get there, and then under file, new notebook.
Click the details. Let's see.
And this was like gibberish, to me at least.
Text encoder, not. Yeah, it looks like. What browser are you using?
Edge.
Edge.
Maybe try different browser.
That's a new Internet Explorer browser, right?
Yeah. Do you have a different browser?
I don't think I do actually.
Okay, because I'm using the Chrome.
Yeah, I don't think I have another browser.
Okay,
I'll have to download one.
Then you can maybe try a different browser, see what you can get there. Okay.
Yep, sounds good.
All right. So now go back to my screen. All right. So everybody get this Colab working. Let me get rid of some of this stuff I have. Okay, now go back. This page you should be able to get there, right? Without the Colab. This is just a link to this web page. Matthew.
Yeah.
You'll get there.
Yes.
Okay, now you can maybe just look at my screen now. Let's go through this. Okay, towards very end, if I screw this all the way to the end, at the very end you say, okay, the entire notebook is available here, and then this will link you to a GitHub page, and you can download this notebook. Everybody get that? And then you download this notebook, try to run it on the Colab after today's lecture yourself, okay? And make sure that everything is working by next lecture. Yeah, make sense?
Yep.
Yeah.
Okay, so now let's go to the very beginning. Okay, so our task is to recognize handwriting. This is the so it's traditionally it's like a hello world to the neural network, hello world to machine learning. Is to recognize this handwritten digit. So So basically say, okay, you have a bunch of digits and you want to create a neural network and able to train the network such that you're able to recognize each writing is whether it's 0, 1, 2, 3, 4, 8, 9. So, and then once you have this network set up train, and then you test it. Okay, so that's basically is what we're doing. It's a little bit more now very detailed exactly what we're doing. So everything is very within the graph of I think this is something that you guys should be able to recreate yourself given your experience so far with Python. And I'm going to talk a little bit about PyTorch, which I only learned last few days anyway. So you're learning this together with me, all right? Okay, so first is the data set itself. So this is the basically example of a data set. All right, so, and you know, this has been collected, of course, there's somebody maintained it since with 100,000, I think what, a collection of 70,000 digits split into training set. 60,000 length is used for training set and 10,000 length are using for like verification or test. Right. So that's the data itself. All right. And the first part is if you do radical lab is to say you do a bunch of library you try to import, you know, like some of them we're very familiar like NumPy, and the Torch Vision is basically a package is specifically created for machine learning. As I said, this is a PyTorch is based on Python, and is the Facebook version of a machine learning platform. And of course, this matplot, you're familiar with this, right? Time, again, Torch Vision, and all things related to Torch is related to machine learning. So this just import bunch of library function, and the first thing is to say when we have a data, you want to have a standardized data input, okay? And what you do with standardized data is this two functions. One is to say is transform tensor, and the other one is transform normalize. So tensor basically, you know, tensor is just a generalization of a vector and a matrices. Right. So vector is a one-dimensional one-dimensional data. It's like array. A matrix is two-dimensional data. High dimension data is just generally called tensor. Right. You can have many dimensions. Okay. And that's, you know, 3-dimension is called 3-dimension tensor. Right. So that's why, and all this machine learning you can see is, you know, you have a lot of intermediate layer. Each intermediate get a lot of input. So all this calculation, if you cast in terms of tensor framework, it just make coding and computation very easy. So just that's all you need to know about the tensor. Right. So basically, say you take an image, you're going to transform into n-dimensional, certain dimensional data, and then this second one is just normalize. So you have pixel, for example. So let's say you take an image, which generally every pixel is represented by red, green, blue, and in general, our image represent 0 to 255 level. That's most of digital image is in that level. And then basically this normalization just basically take any color image and then make it into gray and then normalize the value between 0 and 1. So that's what it does, okay, normalization. So that's what this transform function does. It takes some, whatever image data is doing this cast in the tensor form and then do normalization. And then, so this is this view line loading up the data from the database. Okay, so basically this particular data called MN-MINIST. I don't know, I don't remember what this stands for. Something I don't remember exactly what it stands for, but this is what referring this library has bunch of data, but this particular data is so you is contain all those image, contain this individual image, right? So you loaded these things, and you split into the data is split in two sets. One is a training set, the other one is a validation set, right? So you put it separately, okay? And this loader basically say you divide the training set into batch. So in here is batch is 64, just like what we did in our toy model. The batch is 10. Here I say every time I do training, I run 64 batch and then get average result and back propagate and do training change the weight, and then I run another 64 set of image and so on and so forth. That is basically every batch is one iteration. All right. Same thing with validation. Okay, it's run as a batch instead individual. All right. So this is just setting up, loading the data, split into training and the validation. All right. So this just give you some idea is to take a peek actually what this data look like. This statement is iterated into whatever you loaded into loading into train in the loading set, training set, and then this few line together with this line will spit out a individual image. So I have here, which I did. So I have here, which one I have here? Okay, that's me. Yeah, this. I get too many of these things opening now. I'm confused which one actually I was running. That just start copy. I think there's maybe I just start from here. Okay, so I'm going to run import. Okay, so this is just import a library, and this one just to specify my local Google Drive. So it actually it's download. It's going to download all those data, image data into my local Google Drive. So this is just try to get the name of my local Google Drive, and then and this will start the is this running? I think this I already done this before, so it's presumably is already I already had in my library, and then this is going to show couple is show the data has a 64 batch in size. The image itself, each individual image is 28 by 28 pixel. Okay, and here just show one example. The first image, for example, this is the first image would look like. It's in this every time. So this is the first image. All right, it's 28 by 28 pixel. Okay, and here, for example, is print out a 60 image. So this is what the 60 image look like, right? Just example, just iterate through this thing, you get showing up 60 image, right? So this is essentially setting up the data. Okay, we have data in your drive. So try to get to this stage by the next lecture, and we'll pick up on here. And next lecture we start talking about how to set up network and how to look at the and presumably you guys should be able to set up this. You generally are much better than me. I take me many hours to get here, but probably much easier for you guys. And any questions?
No.
No.
Yeah, no.
Oh, it's not. Then that's about it today. You can play with the playground and then get this Colab scenes. Download this from GitHub and get this thing running on Colab. All right.
All right.
Okay. That's all. Everybody's doing good.
Yeah.
Yeah.
Doing all right.
Yeah.
All right. Have good spirit. Now we are being home quarantined for 3 weeks. Keep your spirit up and do exercise.
Yes, exercise is very important. Well, like
Okay.
people are forgetting that, you know.
Yeah.
People are restricted. I had to go to Walmart yesterday, and the amount of people that like think that they can just throw on a mask and be invincible is just amazing. It was
So people are
disturbing,
not
really.
wearing masks?
No, people are wearing masks and wearing gloves, you know, but like that's like not the important part. The important part is to stay away from people.
Yes.
You know, like with that
Well,
that
it's
whole
not
6
just stay
feet,
away
7
from
feet,
people. The very important is to say, try to avoid touch the surface unnecessarily.
and
And then
also
if
your
you do touch the
face.
surface, and then make sure you come home, don't touch your face before you wash your hand. That's really the key.
Exactly. No, and that some people just, you know, they just like still want to like get close to you. You know, it's like going to the grocery store. You want to pick out some lunch meat or whatever, but like